Wesley, will you just admit the people to the webinar? Can you?
Okay.
Thanks. Good morning, ladies and gentlemen, and welcome to ACTOM Smart Technologies' webinar on Powering Tomorrow, AI-driven transformer maintenance and smart technologies. ACTOM Smart Technologies is a market leader in supplying protection, metering, and low-voltage solutions to the electrical industry. The offering includes a comprehensive range of automation systems, protection relays, credit, smart and prepayment metering systems, and hosted services, as well as LV motor control centers and power DBs, variable speed drives, condition monitoring, smart solutions, drone inspections, and components and accessories. Before I introduce our speakers for today, I just remind you to ensure your volume is turned up on your device and ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. A recording of this webinar will be made available on the SAIEE YouTube channel under SAIEE TV, and you will find the registration link in the chat box. Please register to receive notifications. It is free. So let me introduce you to the team today. I'm going to introduce our presenters first, and then they're going to go over in their presentations. Our first presenter is Goodness Maziya. She's a metering manager at ACTOM Smart Technologies. Goodness as a manager at ACTOM's metering, power quality and related projects, overseeing manufacturing and compliance. She specializes in advanced metering and power quality, leading large projects and meter initiatives. Goodness has a bachelor's and master's degrees in electrical and electronic engineering from Northwest University and is passionate about smart technologies transforming energy networks. She focuses on sustainability and innovation, showing how smart metering can help municipalities deliver reliable, efficient services. Our second presenter is Wesley Vorster, who is a digital solutions manager at ACTOM Smart Technologies. And Wesley leads ACTOM's digital solutions, advancing automation and monitoring through strategy. He develops digital solutions that enhance reliability and enable predictive maintenance for utilities. With a decade in automation, Wesley integrates hardware with digital systems for IT and operations. Wesley is pursuing a Bachelor of Commerce in IT Management and has specialized training in industrial IoT. He focuses on scalable AI and analytics-based monitoring solutions for smart networks. And our third presenter today is Andrew Yates, Director and Chief Technology Officer of Quill Technologies. And he's an entrepreneur, solutions architect, and CTO with over 3 decades of experience turning complex business challenges into elegant, data-driven solutions. His career has always centered on one constant: leading engineering teams to build purposeful technology that delivers measurable outcomes, whether through efficiency improvement, risk mitigation, or sustainable competitive advantage. After an early career in managed IT services, Andrew co-founded Chronologic and subsequently Quill Technologies, redirecting his expertise towards the industrial and manufacturing sectors at exactly the moment those industries were being transformed by IIoT, cloud computing, and business intelligence. So we start off today's presentation with Goodness Maziya. Over to you, Goodness.
Thank you so much, Mings. Good morning, everyone. I am now going to share the presentation on my side. Okay, it seems I have problems sharing. Wesley, can you please share on your side? Thank you very much, Wesley. Thank you very much, everyone. Thank you for joining us today. We hope that the presentation is going to be helpful to every one of you. So as mentioned by Mix, I'll be looking at the smart metering side. I'll be highlighting on how smart metering, when combined with AI, can transform South Africa's energy sector. So smart metering is no longer just a technology trend. It is a critical enabler for revenue protection, energy efficiency, and grid reliability. For utilities across South Africa, especially those that are under the pressures of financial and operational pressure. So smart meters provide the visibility that is needed to manage consumption and improve collection. Hello, am I visible? Am I audible?
Yes, you are. Please
Oh,
proceed.
okay. Thank you so much. So smart meters gives us the data, but AI transforms that data into actionable intelligence that strengthens the grid and support a more resilient and just energy future. Proceed, Wesley. So if we look at where we are currently in terms of the implementation of smart meters across South Africa, with a focus on municipalities and ESCOM, since there are the two main domain players in the sector. In municipalities, we have the leading metros like your Tshwanes, where they are implementing smart meters. They are actively rolling out smart meters and focus more on the commercial industrial customers. We also see that they are metering their feeders at secondary substations. If we also have the mid-tier or mid-sized towns or municipalities that are in the mid-sized towns where they are passionately rolling out the smart metering, and the focus is more on the revenue protection in high loss areas and major feeders. But the implementation tends to lack a bit in terms of the full back-end integration. We have another category of where the municipalities are in the rural areas or under-resourced category, where they are still reliant on the manual reading of these meters. Eskom, on the other hand, is actively rolling out smart meters, and they have a target of installing over 6 million meters by 2029. And their deployment include full back-end integration, and feeder metering is being introduced at secondary and higher voltage points. So while progress is being
That was
made, the rollout is quite
Sorry,
uneven.
goodness. Goodness, sorry.
Okay.
Anybody who's unmuted, please mute yourselves. Thank you. Please proceed, goodness.
So while we've seen that there is progress that is being made, it is uneven. The rollout is quite uneven, with advanced systems in some areas and with partial solutions in others, and many communities are still reliant on outdated manual processes. Firstly, so now if we look at why we have the uneven implementation of smart meters across South Africa, why are other sectors lagging? It's because there are challenges that they are currently facing. There is that of the high upfront costs associated with the implementation of such systems. We have problems of connectivity, where you find that there are areas that struggle with mobile coverage. We also have some municipalities are facing challenges of skill shortages. They don't have the staff that is have the skill to implement and manage such platforms. The other one is that of the tampering and stealing of SIM cards and smart meters. So we have that is why there is the uneven implementation of smart meters across the sector. But despite these challenges, we cannot afford to delay the implementation. We would rather try to explore solutions to address these challenges. So if maybe there is a challenge of that of the high upfront cost, we can then try to roll it out, have a phased approach or phased rollout. And if there are issues of connectivity in some areas, we can then implement hybrid communication technologies so that there is sort of like a backup in case there is a communication protocol that is not working at that specific point in time. And issues of unskilled personnel, we can roll out training programs to capacitate the staff and ensure that they're in a better position to implement and manage these platforms. Wesley, sorry. So when these meters are implemented now, is it advisable for them to communicate? When these meters are implemented, is it advisable for these smart meters to communicate directly to the AI agents? Um, the answer to that is not, it's no, it's not ideal. The reason being is the meters produce a lot of raw data that is unstructured, making it difficult to process by the AI agent. So the correct approach is that you will have the smart meters installed. So these smart meters need to send data to a metering management system so that the data can be validated first and organized to ensure that there is consistency across millions of data points. So once that data is structured, it is then passed on to the AI agents for deeper analysis. We can use that data for to detect anomalies or focus the demand or do predictive maintenance and identify any revenue losses that we might be incurring. So this structured approach allows the AI agents to deliver reliable, actionable, and um, insights, ensuring that the AI agents are not overloaded. So while these smart meters are the source of the data, it is the management system that actually prepares it, and only the AI can then unlock the full potential of the data. Wesley, so when I'm done, you can just move on to the next slide. So now we've different systems that we have. This one just shows the different systems that we have deployed across the sector. So each of these systems has a specific purpose or a function. So we have the smart meters that are built to measure consumption and billing. We have SCADA for real-time grid monitoring control. We have DMS that is focused on grid operation and optimization. Then we have the AI analytics that are designed to provide deeper insights and prediction and be used for automation. So the key here is to actually let each system do what it was designed to do. Because when we tend to use systems outside their intended purpose, we then dilute their effectiveness and we miss the full value of the data. So by keeping the measurement and monitoring and operation systems within their respective purpose, we then allow AI to process and interpret the data so that we can have real potential, unlock the full value of that data. So each system plays its role, and AI sort of ties them together for actionable intelligence.
So they are asking what for.
So here is a roadmap. So since now we understand that the role of AI, we now have an idea of what the role of AI is smart metering. So now the next question will be then how do we actually get there? Where do we start? So we need some sort of a roadmap, which is this one that we can use. So the first phase that we can actually start on is that of doing an extensive audit of the existing infrastructure so that we can have a true technical and non-technical losses of the grid. And once we have that, we can then do conduct pilots on targeting on the targeting high loss feeders so that we can have immediate impacts, and then once that it's in place, we then have to deploy the AI on the pilot so that we can have data that can be used for decision making. So now, after having sort of like proof of concept, we can then roll it out on a larger scale. We expand the coverage, so that we can have visibility of the entire grid. But a roadmap alone is not enough. We need to sort of have like collaboration between the different stakeholders, like your ESCOM, municipalities, your IPPs, regulators, and communities. We must all align so that we can make the vision of smart metering implementation a reality. So the path is clear. We need to do just an audit, we then pilot, we deploy, we then scale up together so that we can build a resilient and just energy future. So if you look at, so here we sort of like have real examples here in South Africa. So this is not theory, it has been implemented already. We have Tshwane that is used AI agents to in their system. And the meter reading accuracy is actually improved from 27% to over 80% after the integration of the AI on their existing systems. We have Plentify that is assisting households manage energy. There's ESCOM that is using AI for national grid optimization, and there are academic aspects that are shaping tariff modeling and reforming policies as well. So these examples are sort of like proof that the AI-driven smart metering is not just a theory, but it's actually happening, and there are stakeholders out there that are actively rolling out AI agents onto their existing systems so that they can get full potential from the data. So that concludes my section. So we've seen how smart metering and AI can directly address current challenges, from revenue protection to DR integration. So now I'll hand over to my colleague Wesley, who will then dive deeper into how the AI agents work and its architecture. Thank you very much. Over to you, Wesley.
Thank you, Goodness. Okay, so before we start with the AI portion of this presentation, I think it's essential to understand how we enable the AI agents to come up with these insights for us. So it all starts at the beginning, obviously, with the data acquisition. With the data acquisition, we follow a very simple process, and I think most people do. It's connect, collect, store, analyze, visualize, and improve. The first and the last being as important as all the rest, but the connect is really where the big divide is in South Africa. As Goodness alluded to, there is a big information gap between our networks and the data that we can or possibly extract from those from that equipment. Just a quick overview of how a smart metering network would look. Very, very simple, obviously. But just to show where the meters would sit, and then between these meters, we would be able to pick up if there were any wrongdoings or issues between the different points in the system. Okay, so going back to the connect, collect, store, analyze, and visualize, it all starts with the collection of the information. This can be done through various sensors like meters, but also a lot of other types of sensors that you can push through a edge gateway to basically give you a breakout into the internet so you can access it remotely. You don't have to go to site to get your information. Collecting the information, we talk about data normalization and optimizing the data captured. Like Goodness said, meters push out a lot of information, and we don't necessarily need all that information. We could if we're storing it in a historian, but we would put it as a periodic polling type of architecture where we would get information every half an hour, 30 minutes, just to give us a good resolution of the data. Then what we also like doing for alarms and notifications of critical issues, with edge gateways, we can set up a report by exception alarm. So it would poll normally until there's an issue. It would then highlight that issue and push that to the database. Between that sits what when we get to the store part of it, it sits the UNS. The UNS basically works as a centralized real-time data hub for systems to subscribe to and then show that to whoever needs it. Centralized meaning that we could have our dashboards connect to it and get live information. We could have AI connect to it and have access to that live data. So when we get to the database could be anything. It could be a SQL database. It could be a OPC UA server. There are a lot of different ways to store the data. But then the UNS basically structures the data according to the ISA-95 standard. So that standard just gives us a rough architecture of how to structure the data so it is a bit more palatable and easier to digest. Okay. So it starts at the top level, enterprise. We might have a municipality's name there, and then we go down to the site. Because one site might have 10 meters, we could have the specific equipment listed there. Let's say you have more than just a meter, you have multiple different sensors like a substation. You would have your transformer monitoring and the metering from the incoming feeders and data. Then we can have it on the instrument level. So if there's a single sensor that has a temperature probe that's giving us a bit of data, we can structure that into the hierarchy of the data structure. Okay, then getting to the analysis part of it, that is where we work with the data to give us insights. Raw data is very, very difficult to interpret if it's not structured. The UNS helps with that, but with the refinery part comes the insights. So with this, we can do time series analysis. Time series analysis, very important, obviously. That is very important for troubleshooting. We need to know what happened in what order to give a good resolution to the problem. Okay, then visualizing. This is the dashboard that pulls the data from the database and shows it on a clear screen. Okay, then a bit about the agents. So the thing that makes agents so good is that it has access to a lot of understanding or context. AI agents, where we used to look at AI as something like machine learning, that is only one of the types of AI that you get nowadays. I think the last time we checked, there were 250 something odd different technologies. But AI agents have access to all those technologies, which is a big advantage for it, because you don't need a specialized person in machine learning or a specialized person in computer vision to get a solution up and running. Important to note here, AI agents, the reason why we say agents is because an AI agent could work with multiple other agents, basically creating an agency. So you can specialize the agent to do a specific task. Like we have here, we can see there's a transformer health agent that's gathering all the data and reviewing periodically the transformer status. We have a cybersecurity resilience agent here. We have a fraud and theft detection agent here. And all of these are going to start implementing actions according to what it sees in the data. Yeah, I just wanted to quickly show how this connects up with the database. The database, we basically just give the AI agent access to the database through a MCP connection or server. This then coupled with the with other knowledge-based information, so specifically IEC standards or company-specific standards, it gives the AI agent more context to write more informed, detailed reports or actions. SLA KPIs, it can track that for you same time. But then as an output, the AI agent could, for one, log a ticket to the maintenance team if it thinks that there is an issue that needs urgent attention. It can also write reports, so scheduled reports. You can make the reports as standard. It always gives you the same information, but the value really lies in that it can give you a report that is specific to what would be important to know. If there's something big, it highlights it very nicely. And you'll see that in the demo that Andrew's going to do for us. Obviously, with AI comes a lot of issues with trust and cybersecurity. There are ways to mitigate these. I think we are past the point where we just dismiss AI completely as an untrustable source of information. Yes, it still has its issues. There are issues like the hallucinations that can be worked out. But also we need to make sure from our side that that information is secure. All this information that we are sharing with the AI is either IP, which can get you into a lot of trouble if it gets out, or yeah. So getting to keeping it secure. Obviously, IEC 62443 is very important for the connectivity side of things. Understanding that the network is secure and cannot be breached from any point in that network from edge to core. Data loss prevention from a user interface point of view is very important to ensure that employers are not adding documents that they shouldn't be to the AI. Helps with document control and helping with that. Well, I can ask anything on AI. Encrypted data, obviously making sure that the data is encrypted so that it can't be sniffed or it can't be taken out of the data stream or manipulated for that matter. Then having it be explainable. So this is another big issue, especially with engineers. Making sure that how the AI got to its conclusion is the right path to take. Obviously, you have all that knowledge, you have all the context. So there are ways for you to have it explain how it got to the solution that it did, why a certain issue might be an issue. But then also you get systems that can track the explainability side of things, systems like Lime and there was another one as well. And then the most important thing about AI, there has to be a human in the loop. Even though we are getting to trust AI, we still can't trust it 100%. And it's experts like you guys that we need to make the final call, do the approval. But AI is there to help us make our lives easier. Okay. I'm going to hand over to Andrew now. He's going to do a demo for us on one of the sites that we did. As a POC, he will go over some of the information again, but maybe in a bit more detail. Okay, over to you, Andrew.
Thank you, Wesley. Just getting set up on my side. And just let me know when you can see my screen.
Yes, we can. Thanks.
Okay. Okay. I just wanted to loop back to something Goodness mentioned in her presentation around raw data is not really that useful for agents. What I'm going to do is explain how the digital infrastructure architecture creates value out of the raw data. If you imagine the digital infrastructure is a refinery, imagine that the raw data is crude oil and the actionable insights is the refined fuel on the other side. The infrastructure is what we need to build to be able to convert the raw data into normalized, contextualized, and enriched data that the AI can use to make effective decisions. So what I'm going to do is I'm going to recap quickly on the connect, collect, store, analyze, visualize, and use it in the context of, imagine you're building a house. The first thing you need to do, you've got all this data sitting in the machines. It's idle. You've got to, the foundational layer is to connect and start collecting that data. Otherwise, it's in a silo and it's of no use to anyone. Then we'll talk about the unified namespace, a little bit more about how the data is organized and some functions inside the UNS. And then I'll explain the actual demo that we're going to do. I'll explain what it is relating to a real solution that, a real condition monitoring solution that we built for one of ACTOM's divisions to monitor the transformers. We'll walk through the schema and I'll show you a live unified namespace with real-time data flowing through it, so you can actually understand what does a UNS look like? Is it a database? Is it a file? What does it look like? I'll actually show you what that looks like. And then at the end of that, we'll show you how the architecture gets expanded to allow us to sit alongside AI agents and work with humans to get powerful insights out of the data. So Wesley's already walked through the high level of the architecture. Only thing I'd like to add here is, in terms of the UNS, imagine a unified namespace as a semantically organized inverted tree, where every single piece of data, real-time data, has got a location, like a street address, on a street, in a suburb, in a city, in a province, in a country. Everything is referenceable and indexed. So if you need a temperature reading, an ambient temperature reading of a device, of an environment, you can find it. You can find whatever you want. The unified namespace has got three main types of data that it stores. There's definitional data, which is static data. Imagine the serial number of the piece of equipment, or the manufacturer, or the install date, or something like that. That would be definitional. Informative would be information that has been derived from the raw data that you would use to create visualizations. So that data could be what finds its way onto a report or a live dashboard. A functional areas are things where you deriving data, you're creating new data from raw data. An example of that would be, I want to automate calculating the overall equipment effectiveness of a particular machine, and from the inputs I can calculate. So I've got in-feed, out-feed, waste, and machine state. From those raw inputs, I can calculate the availability metric, the quality metric, and the performance metric. And inside that UNS, underneath that device, in the right level of the hierarchy, I'd have a little placeholder called OEE, and inside there I would store a percentage that could be calculated at the end of every minute, every hour, every day, and that could be contributing to the richness of the information that's being stored that can be then analyzed. Okay, let's move to the next slide. Okay, so now what I'm going to explain is the real example. So for these power transformers, the business case for building the solution was to minimize warranty period risk. The customer didn't have any digital record of how the equipment was being operated in the field. And when things went wrong, there was no way to diagnose what happened or to be able to determine whether there was noisy harmonics from the generation side or there was over demand, they overloaded the transformer, whatever it was. So what we did was we built a real-time monitoring solution around 5 essential inputs, 3 main ones. The dissolved gas analyzer gives us readings of gas concentrations in the oil. There's a power analyzer that tells us about the quality of the power on the generation and the consumption side of the transformer. And then the thermal management information comes from the cooler controller. It records temperature gradients, which is really important for the health and well-being of the insulation in the transformer. And it records the useful remaining life of the transformer in the paper insulation. And then we've got 2 additional metrics. The edge device Wesley mentioned that collects the information and does some data operations to convert that data into usable structured data. That little industrial computer, we want to know that that's healthy and it's not running out of memory or it's not overheating. So we've got data on that, and we've got some weather data which the customer can then use to correlate poor generation days with weather and high cloud cover, etc. And in the example, it's very simple. We've got in the UNS structure, we've got an organization called APT demo. I'm going to just point over here. So this is the root organizational level. And then underneath each of these, we've got a site, one called Richmond, one called Loxton. And then within each site, we've got a transformer ID, because we could have multiple transformers at a particular site. So we want to be able to accommodate having multiple transformer IDs below the site. And then within there, the instruments and their particular readings and weather data. Now, what we've done is I'm going to show you data. It's important that you understand the data that you're going to see is simulated data that's updated every 5 seconds based on a random walk simulation with values drifting gradually or more aggressively depending on the type of data it is. So that this is a simulation. I can't obviously show you real customers, real data. So that's what we've done. We built a simulator that sends that data through. This is the hierarchy of the actual unified namespace. So on the left, you can see the organization and then the site and then the ID, transformer ID. And then we've got the dissolved gas analyzer, the cooler controller, the power analyzer, and the device health, and then weather data at the site level. And you can see how if I had 100 transformers and 50 sites, this hierarchy this design would accommodate an infinite number of sites or transformers because the schemas are exactly the same. And in this particular screenshot, we've got the dissolved gas analyzer data. And here you can see how the data would be structured. It's a JSON string, which is readable, easily human readable. So you can see a timestamp because the messages come through every 5 seconds. We want to know what was the date of that reading. In case that message got delayed in transit, we want to preserve the timestamp on the message. It's got the equipment ID and the site and the instrument name, and then it's got the gas reading category, and then it's got your concentrations in parts per million. Something important to understand here, this is an example of non-normalized data. Normalized data is data that you can act on. So this carbon monoxide to 281.9, you don't really know what it is until you give it a units, parts per million, you can't act on it. So what the UNS does and the data operations does is it adds that layer of context to the raw data that's coming in. It may do some calculations. So in this case, it would do, there's specific gas ratios that are important that trigger alarms. So we'd get the raw data in. There's a data operations function that will calculate the new, whatever the ratio is, carbon monoxide to methane rating. That would mean something to the engineers. And if it's over a certain level, that would be saved in the functional namespace and it would trigger an alarm, for example. And then on the right is just a, let's say, a dashboard view of how that data would be interpreted in a real world example. So what I'm going to do now is I'm just going to quickly switch to the unified namespace live data. Here we go. Okay, so what we're looking at here is real-time data flowing through the UNS. And I've deliberately collapsed the hierarchy because I want to expand it and explain one step at a time. So if I expand, in this case, Richmond, I can see weather data. If I click on weather data, I can see the last message came through at 10:41:13, and now there's a new message at 10:41:18. So I know this is set up to refresh every 5 seconds. So if we wait, we'll see it go from 23 to 28. There we go. And we've got new data, and the data is being adjusted gradually as you would expect a weather data to do. It remains fairly consistent, but there are changes. So if I look at the ambient temperature, any of these, you can see it's slowly walking up or down based on the simulation. Now, if I expand the transformer object in the hierarchy, now I can go and click through, look at the device health. I've got the storage utilization, the memory utilization, the CPU activity percentage, etc. Then if I look at the DGA, I've got gas readings. So these are the actual readings coming through, and then the alarm states. So each of the messages that traverses the unified namespace has got a hierarchy, a schema to it, that's understood by the sender and the recipient, and then written to the historian. The historian is the database that's optimized for time series data that will keep the history, and it may have summarization rules that remove or summarize data that's every 5 seconds after 12 months to every 1 minute, or after 36 months to every hour, so that you're not storing a runaway data growth that you're going to run out of capacity. So that's kind of what happens on the back end. So if I click through any of these, you can see the cooler controller's data is coming in every 5 seconds. And in your, once you've built your unified namespace, every object will have its refresh rate. You could have an alarm state that's updated only once every minute. You could have very high resolution data about, let's say, a position sensor that has to be every 5 milliseconds, so that you can, because of the nature of what you're doing. So the frequency with which you ingest the data depends on the application and what you're trying to do with it. Okay, now I'm going to go back to my presentation and go to the last slide and explain how this gets connected to agentic AI, and how do you unlock the power of this amazing system that you've got built that's giving you real-time data and dashboards. So in this drawing, you'll notice on the right-hand side is what I've shown you. Basically, you've got your transformer and you've got your real-time data coming in. And this is let's say, a contained system. And no one on the internet knows anything about it, but you want to be able to make decisions based on this data. So how do you get access? How do you give your ChatGPT or Claude or whatever model whatever tool you're using, how do you give give your agent access to that information? Well, what you need to do is you need to implement a translator that sits, an intermediary, like a proxy, that sits in between your agent and the system, this bespoke system that you have. That agent is called a message context protocol server in this case. So we built a custom one because we had to, because this system, we're the only ones who know kind of, but we built it. So we can't go and buy an off-the-shelf MCP service for this system because we built it. So we had to build our own MCP server. And inside the MCP server, there's a tool registry, there's input-output schema definitions, there's descriptions and functions, and API calls and database query samples. It's all the things that the AI agent would need to reference, like a user manual, to understand what intelligence and data lies beyond that MCP service. So think of it this way: your MCP service and your condition monitoring system, if you draw a line around it and a bubble and you gave it a label, that could be your small language model that your agent is using to help you answer questions and solve problems for your business, your small language model. But it needs the large language model to understand the human natural language queries that you're going to be sending it. So now what I'm going to do is I'm going to actually show you this in action. So I just need to connect. What I also just need to explain is I'm using Anthropic Claude for the demo, but you can use any agentic agent that supports MCP server connections. So it could be ChatGPT, Copilot, whatever. I'm just using Claude. So it's just an example. So what I'm going to do is I've got some sample queries. And the first one I'm going to run is I should probably just show you this quickly. If you look in your agent under connectors, you'll notice there's a bunch of connectors you can add, and you can go to the AI agents libraries. I've got lots of off-the-shelf connectors. These are really MCP services that are publicly available that you may want to implement for SysPro or SAP or whatever cloud service maybe that you're subscribing to. What we're doing here is we've got this InfluxDB MCP service connector. So a connector is a digital coupling to an MCP service that gives the agent access to a system. And you can have more than one connected at a time, and we'll come back to that now. Okay, I want to go back. Okay, so what I'm going to do is the first query I'm going to give the agent is I'm going to ask it what assets are connected to the MCP server and what types of data can you get from it. So it will use the large language model to understand the English, and then it will use the MCP server service to answer the question. This little screen at the bottom left is just showing traffic to the MCP server service. So when I ask it a question, it'll actually, in the background, it's busy sending queries and getting information back from the MCP service, which the MCP service is getting the data from the raw database. So it's telling me that I've got one transformer asset in the pilot that's behind the MCP service, and it's telling me what the asset UNS name is. So it's APT demo is the organization name, the site is Richmond, and the serial number is 3035211-01. It's telling me that I've got dissolved gases. The readings are called DGA gas parts per million readings, and it's telling me all the different types of gases that the DGA can tell me about, including water content. It's also got gas ratios, it's got alarm readings, IEC standards alarms, etc. It's got thermal data that it can tell me about, humidity, ambient temperature. There's also wind direction and a whole bunch of other ones. It's got electrical quality of the power going through the transformer information and so on. So that's what's available to me. So I'm going to start with a simple question. I'm going to ask it, what is the current top oil temperature on the transformer? So if I go to the dashboard and look at the updated data, top temperature for 46.6, it should come back with that as a reading. There we go. It's giving me a whole bunch of other information. It's telling me about temperature differentials, and how it's changed over time, and how the calculated winding hotspot temperature is also the same, etc. And some analysis on it that I didn't really ask it for, but that's fine. Okay, the next prompt I want to give it is, what is the remaining service life of the transformer? So we'll cheat and go into the dashboard and have a look at what that is. So if I go to the cooler controller, it's going to tell me remaining life 100%. So let's see what it comes back with. Okay, 100%. Life consumed 0. So it's a recently commissioned transformer. Okay, now I'm going to give it some prompts that it has to do a little bit more thinking. Give me a quick health summary of the Richmond transformer. Cover temperatures, active alarms, and remaining service life. So just to clarify, in production, you may have automated processes that are issuing these queries to the MCP service. For the purposes of the demo, I've got my agent open and I'm copy pasting the queries straight into the window and waiting for a response. But I could have a scheduled task that pulls a monthly health check, a daily health check, and mails it to me. So I don't have to sit and wait for it. I can embed or weave the functionality of the MCP service into any software or automated process or script that I want to. Okay, so it's given me an overview. Now I want to drill a little bit deeper. I want to check the dissolved gas analysis. Are there any gases that are concerning? If any, what do the readings suggest? Okay, check the dissolved gas analysis for the Richmond transformer. Are there any gases at concerning levels, and what fault condition, if any, do the readings suggest? Something I didn't mention earlier, this is a Claude project. So I've attached some domain expertise documentation to the project that it can reference. So if I've got, if I want this to function as an expert in a specific type of transformers, I would give it all the knowledge documentation in the project that I could, so that when I give it a question, I don't have to be specific, or I don't have to be the domain expert. I can rely on the agent to reference the deep domain expertise knowledge in the attached documents. I can also give it instructions, how I want the outputs to be. For example, I might say, when I ask you something, always create a dashboard for me, or always create a Word document or an Excel sheet. Okay, so as we're going through the examples, they're getting progressively more work for the agent to do. So the response times are getting longer, but hopefully for the purposes of the demonstration, it's a bit more rich in terms of explaining what it can do and how it works. So what I like about Claude is it is telling me every step of the way. It's going, I'm thinking about the DGA analysis. Then it's going, I'm investigating the CO2 level. So it went and pulled the latest DGA readings over here. And then it got a broader historical view to understand the trajectory. Now it's producing a kind of an on-the-fly report. I didn't ask it to do a report or tell it how I want it laid out. It's coming up with a format for me that it thinks will be useful. So what I could have done is I could have given it a sample report and said, use this as a template, and it will produce that report with exactly the same layout and font and everything. Okay, so I can see here it's analyzed the readings, and it's highlighted carbon monoxide as an anomaly, and it's given me a breakdown of why it's a concern and what is an acceptable level, which I'm not a transformer engineer, so I'm the operator, but it's telling me that it's at that level, 670 parts per million, and whether that's acceptable and what I should do with the information, why it's a key concern, etc. Okay, and then the last example, I'm going to ask it to do, I'm going to say I need a concise executive briefing on the condition of the Richmond transformer. Assume that the audience understands the business risk, but don't need the technical detail. Okay. What we use this for, yeah, please go ahead if you've got a question while we wait.
Thank you, it was unmuted.
Okay. What I could do, what I was going to do, but it just takes a bit long for the purposes of a live demo, is I've got a domain expertise standards document sitting here, which is the IEC 60599 standard for these transformers. And what I can do is I could give it this document, which is a lengthy document on all the deep technical expertise that is required to ascertain the health of a transformer. And I could upload that to the agent, and I could say, use this IEC standard to produce a detailed report of the transformer's health over the last 36 months. And it will go away and spend 20 minutes, half an hour building a detailed report for me. So let's just go back to this. Okay, it's still busy diagnosing. So just the other point to add is one of the big business benefits to having this technology is that if you were to do that kind of analysis on a wide range of transformers manually, you'd need many qualified engineers to do a lot of manual work, reading and doing and writing reports. So what this allows this particular division of ACTOM to do is to scale the number of transformers under management without necessarily scaling the number of qualified, experienced engineers that know how to evaluate the health at the same rate. So it kind of future-proofs, and they can, let's say, codify the engineer's expert knowledge into a system that can work next to a smaller number of highly skilled engineers, can do the work of an army of engineers, let's say 50 or 100. Okay, it's pulled the readings, it has all the data, and it's now building the executive briefing. So just going to maximize that. Assembling the briefing, formatting. go. So it's highlighting that carbon monoxide event or trend. It's giving me temperature, weather, health, power, export statistics, and so on. It's giving me my gas ratios and highlighting what is normal, what isn't, key findings. So it's telling me the CO2 event surged from 6 parts per million to nearly 700. I can tell you that the instrument is recalibrated, so it's not a real problem with the CO2, the CO reading. It's actually a recalibration of the instrument that caused that change in the reading. It doesn't know that, but I know that. So that's why I'm just explaining it that way. So it's telling me about the paper and what the CO2 CO ratio dropping, what the implications of that are, and it's making recommendations. It's saying we should increase the monitoring cadence for the DGA data, maybe commission an oil sample and a furin analysis, review the hotspot winding alarm thresholds, etc., etc. And I hope that gives you an idea of how we get from connect, collect, store, analyze, visualize to that next layer on top, which is adding the intelligence and enabling humans to work next to agents to get more out of the data. I'm gonna stop sharing and then open the floor up for questions, maybe.
Thank you very much, Andrew. I appreciate it. It was very, very informative, and I'm sure our attendees also would think it's very informative. If I can ask you now to please post your questions in the chat box, and we can answer that. Let me just minimize this so I can get to see the questions.
Yeah, I'm watching the meeting chat, so let's see.
Okay, cool, great.
Yeah.
Thanks.
Okay, cool. While we're waiting for questions, the other point I wanted to make is when you're motivating to the business to build the refinery for the data, the businesses probably needs to see the long-term vision and understand how you go from raw data to normalized and actionable data to the agentic AI integration, that it's quite a long tail to return on investment, because it's quite expensive to run cabling and integrate and start pulling raw data out of PLCs and instruments. That part often takes the longest and is the most expensive. Once you have connected all the endpoints and you're collecting and you've designed your unified namespace, then the hard part is done, but then you can only start really benefiting from the insights. Okay, the first question is, I saw we are using quality of service 0. That's just for the purposes of the demo. So obviously your infrastructure would need to be set with an appropriate quality of service for your environment. So good point. Yeah, just for the purposes of the demo.
Then Andrew Boyer asked if you can just show him the dashboard again.
Yes, okay. Let me just share. Okay, so let me zoom up. So the condition monitoring solution is really an industry 4 type application. So it's real-time data presented in a way that decision makers can make decisions on it. So in this case, we've got dashboards, reports, alarms, and historical and instantaneous data. So we've got an overview panel which shows a portion of the cooler controller information, a portion of the power analyzer data, and a portion of the DGA, but not all of the data, and some weather data. So here I can see I've got, let's say, cloud cover, and then I can look back at the last 7 days on cloud cover, and I can compare my cloud cover to my power output. And I can see, oh, when there was lower generation, then I had high cloud cover or whatever. The power analyzer data is for deep analysis of power, and it's some parts of that data in the overview, but this is more of a deep dive, so it shows harmonic distortion, etc., etc. I don't want to spend too much time on the detail here. Cooler controller tracks temperature gradients and the life, and alarms. So these things are fans coming on, fans going off, which will align with the maximum temperature, calculated winding hotspot temperature. So you'll see where the fans are on, the calculated winding hotspots are at their peak. So we can analyze that. Dissolved gas analysis, we've got the red ones are combustible. Those are the very nasty ones we want to watch. The blue ones are non-combustible, and then we've got our water content, and then the alarms for all of those. And then the power events, if there's a fast transient or a voltage spike or something like that, an interference, what we're doing here is collecting, this is a dip, and we're exposing the waveform for that particular 500 milliseconds so that the engineers can go in and see which phase or how did it trend and do analysis on the data.
Andrew, can you see
Yeah.
the Q&As? There's quite a few questions in the Q&A section, or you want me to read them to you?
Yeah, maybe just read them to me, please.
Okay, so we've got a question here from Amish. Have you compared the cloud conclusions to that from engineers?
I beg your pardon, how do we correlate?
Have you compared the cloud
Yes.
conclusions to that from engineers?
Yes. So this is a good question. How do you avoid hallucinations? So there's multiple things you can do. You can have multiple agents, different agents, triangulate their output. So in this case, you could have the same prompt with the same instructions and the same library of domain expertise. ChatGPT and Claude, you could give it identical prompts, and then the responses, you can take those responses and you can put them into a third AI, and you can ask to compare and then alert if there's a difference of opinion. But in reality, what's happening at the moment with this is the engineers are using this, the ACTOM power transformers engineers are using the tool to get the outputs, and then they're manually validating. So they're doing a manual validation because it's about building confidence. Does that answer the question?
I'm sure it does. Amish can just add to make a comment if he needs another question. But here's another question from him. What is the value of transferring data every 5 seconds? Gas values in the oil change very slowly over a long period of time.
Yeah, that's like the quality of service question. It's just a demo. So it would be no value in showing you a live UNS with data updating every 4 hours, which is what the dissolved gas analyzer data does. So this is for the purposes of the demo. We just said we're going to let it update every 5 seconds so that the audience can see what happens when a change comes through rather than have to wait long periods of time. So yes, in production, we definitely wouldn't have a cadence or a refresh rate of 5 seconds.
Thank you. We've got a question here from Rostislav Mayagov. Apologies for the mispronunciation.
Yes.
I saw that we are using QoS 0 for the MQTT communication. Why are we not using at least QoS 1?
Yeah, that was the question I answered earlier about quality. Sorry. It's just a demo. Yeah. Okay. I did see that one.
All right. Sorry. I don't see any other questions that we have.
Okay.
Amish has asked, sorry, a last question here. Have you considered edge AI intelligence rather than sending data to the UNS?
That's definitely applicable for some use cases. In this case, the transformers are sitting in the middle of, in a place where there aren't people that are going to be acting on the the actionable insights aren't of value to a transformer sitting in the middle of a field somewhere with no one sitting next to it. But you would definitely want to tier the analytic outputs where it's applicable. So I would imagine if you've built a digital infrastructure that you've got an engineering team managing a substation, then you would definitely want to do that and do some edge analytics, which you would do. And the other point to add is this is where you would select lower and lower resolution data the further up the automation stack you go. So at the SCADA level or the MES level, you might want to keep the high resolution data for everything. But as you move up the automation stack and that data is finding its way into the ERP system and maybe into cloud, that you wouldn't need to the nearest second or 100 millisecond readings on every single data. You would filter up through the stack. So that's a good question.
Thank you. I don't see any other questions. I'll give it another minute or so. Otherwise, we'll just go over to our thank yous.
Could I take the question from Alvin?
Yes, of course.
So Alvin, the transition literally happens at the UNS. That is where the overlap from OT to IT happens. It's when just before it goes into the database, that's considered IT. Everything before that is OT. But we are seeing that the IT OT convergence is happening as we are getting involved in each other's projects. They are concerned about the cybersecurity of the OT network. So they help us with edge firewalls and stuff like that. And then on the IT side, we want to know more about how we can extract the data and present it. Then just on the questions about project owners, I'm sure we'll share our email addresses. You guys can contact us. Andrew, you want to chip in there as well?
I forgot to mention is imagine your business runs out of a condition monitoring solution or a smart metering management system, but you also run your business out of SysPro and you also have a warehouse management system. How this scales is that you'd expose each of those systems to your agent to expand the small language models that it would have access to, so that you could start to solve problems across all of your systems and not just one closed system, if you understand what I mean. So your agent, instead of having one connector, would have multiple connectors that it can access real-time data that would historically be siloed across the business. Now you can bring them together and start using the data across those different systems. So if you go and Google MCP services for any cloud operators, you'll see there's SAP have got MCP services available. They might not call them that. They might call them AI connectors. Fireflies, there's a long list of MCP services that connect to everything through the service delivery cycle, from CRM, ERP, all the way to and monitoring. Many of those systems are starting to have MCP services and connectors available that you can plug into your AI so that you can expand the scope of what it can access to solve problems. Thanks, Wesley.
And then another question here from Buya. If you have more than 100 transformers, how do you link the MCP to the dashboard with criteria to only bring up critical data so that the operator can contact the engineers and technicians to provide maintenance attention to it without overwhelming anyone with large amounts of data? So that's similar to what we did in the demo. The idea is to get the information the agent to submit tickets to that specific team that's looking after the transformer, and then they would only get a snippet of the information. They do not need all the information. So AI is actually very good with highlighting important information attached to that task. And then, yeah, so they never see the large amounts of data. Only if necessary you can call on it, but you don't need to share everything.
So Wesley, just to add to your comment there, having an MCP service that can see every transformer that's under management for APT is God level access and would be super dangerous unless it's unless only the APT engineers can access it. So in that situation, let's say a customer who has 20 transformers out of the 100, if they wanted to leverage this, we'd build an iteration of the MCP service that is hard-coded not to be able to see other customers' transformers. So you could partition it by MCP service, or if it's a trusted senior engineer at APT, then he'd have to filter using the prompt. He'd have to say, only analyze transformers belonging to customer X, and it would reply. But it's a good point. You'd architect MCP services to partition, or you'd build, or you'd not give the customer agent level access. You'd give them a custom portal that's serviced by the MCP service on the back end, and that portal will only request information for their assets and not reach beyond their assets. Does that answer the question? Cool.
Then
Thank
maybe
you.
in closing.
Yes. Sorry, Wesley, please proceed.
Sorry, Mings. Then just in closing, just to bring it all together, the big thing is to get that connectivity. If we don't have the meters in the fields gathering the data, it is very difficult to create a system to this level or create automation to make it easier to maintain a system. Okay, so even though this was specifically about transformers, it could be anything. It could be the metering. It could be a lower level residential area that you want to monitor. It could be district. It could be whatever you want to make it. Okay.
Thank you, Wesley. Any closing remarks from yourself, Andrew, and Goodness?
Are we just unmuting? No, I think that's everything from me, except to just thank everyone for giving up so much of their time. And thanks to the ACTOM team for organizing.
Excellent. Therefore, I don't know if Goodness, if you want to say a few closing remarks before I end.
Yeah, I think Wesley has already sort of like provided a summary of why we're here today. I would just like to also say thank you very much to everyone that attended this session. We hope that we were able to share insights on the subject matter, and that you'll be able to take what you have discussed today, maybe on your in your day-to-day activities as well. Thank you so much, everyone.
Thank you. And thank you, Wesley, Andrew, and Goodness, for your presentation today. It's extremely informative. And attendees, thank you for joining us today. We really appreciate you being part of this discussion. If anybody has questions and you want to get the recording, please send an email to minx, M-I-N-X, @saiee.org.za, and I will send you the link once it's uploaded on the SAIEE TV. Thank you very much, everyone, and have a lovely day further. Goodbye.